Hello. This lecture is on GANs, generative adversarial networks. And the first thing I want to do is go over why GANs were introduced. What problem was being solved or is being solved by GANs? So the basic problem is when you're trying to model images or sounds. Images and sounds involve numbers, real numbers, numbers that give you the value of a pixel at a certain place or the amplitude of the sound wave at a certain place. And modeling continuous distributions that are very high entropy, like an image has very many pixels and they're all, we think of them all as continuous numbers. Modeling a distribution with a large, very large number of continuous numbers is very difficult. It's different from language. In language, we can have an autoregressive model that predicts the next token one at a time. For an image, the next pixel is a real number. So predicting a real number is different from predicting a particular token. When you predict a token, you can do a softmax over a discrete set of choices to get that probability distribution. When you're predicting a real number, you don't have that softmax. So GANs were developed as an alternative to traditional cross entropy for training models of images. Now, a GAN is going to develop a generative model. So this is going to be different than a model that is based on cross entropy. To use cross entropy loss, here's our definition of cross entropy loss. We have to be able to take a sample of Y from the population. So consider a population of images. So we sample an image and we need to be able to compute the model's probability of that image. Now, if this was a sentence, we would do an autoregressive model, predict one word at a time, and get a probability of the whole sentence by getting a probability of one word at a time. GANs don't provide any way of computing the probability of an image. Instead, the GAN defines a generative model. It can generate an image, and that's all it can do. It can't compute a probability for a given image. And how do we train a model that is purely generative? And again, the motivation here is images or sound waves where we can't use a softmax over a discrete set. So we're going to talk about models that generate images but do not compute the probability of the generated image. And we're going to replace the cross entropy loss that we would normally use in training by an adversarial loss. And I'll talk about that in a moment in more detail. The first thing I want to talk about is how we get a generative model of images. So we build a network that generates an image from noise. So we sample noise. This is typically sampled from a high dimensional Gaussian. So this could be a very large number of random Gaussian numbers, like 1,000 or a few thousand random numbers. Then we take this big random vector and we reshape it as a 4x4 image, say, in this example, over feature vectors that are 1,024 dimensions. So this is generating a 16,000 random numbers. And then we pump that structured noise through a network that converts it to an image. And this network is sort of an inverse convolution network. It's increasing the spatial dimension while decreasing the feature dimension, and then it generates an image. And this probability distribution over the noise, for given noise, this is a deterministic process that generates an image. So for given noise, we get a particular image. So this determines a probability distribution over images. We sample noise, we generate an image. That is a distribution over images defined by the generator. But we don't have any way of calculating the probability of this image. So I'm going to write P sub phi of y for the probability that y is generated when we stick noise in here and apply this network, where this network has parameter phi. The network defines a probability distribution over images. Now we want to train something such that this distribution over images matches the natural population distribution over images, matches natural images. We're always assuming that there exists some population distribution. And we're going to focus on distributions over faces in practice, because that's how this was first done. So I've already said this. We can sample an image, but we have no way of computing its probability. So I just want, this is not a terribly important slide, but it's just giving the equations that define this network. We've seen that convolutional neural networks take an image and decrease its spatial dimension. Here we have an equation for taking weights. This is a kernel matrix at a given layer and increasing spatial dimension. And I don't want to go through this in detail, but there's this observation people make that if you take a network that decreases spatial dimension and look at the back propagation equations that propagate gradients backwards, that gives you a way of propagating in a direction that's increasing spatial dimension. And if you apply the swap rule to this equation for decreasing spatial dimension, you get an equation for increasing spatial dimension. Now it's trained purely in the increasing direction by gradient descent. So this observation is kind of it doesn't matter. It's a red herring. It just is a way of getting an equation that increases spatial dimension. And it's called contranspose. It's just sort of decreasing space in reverse. Okay, now we get to the key idea in GANs. GANs are generative adversarial networks. So we think of them as two players in a game. The two players are actually models, and each model has a job, and they're trained somewhat differently. So what we're going to do is we have a generator that's going to generate an image. We can sample images from the generator. We can pump in noise and sample images. We can, of course, also sample images from the population. Now, if we randomize the generator, the images that the generator produces will not look anything like a natural image. So we train another model to take an image, and we give it either an image generated by the generator or an image drawn from the population. And this other model, called the discriminator, has to determine whether it's a model generated or whether it's natural. Okay, so formally, in terms of equations, we're going to flip a coin. This I is going to be either 1 or -1. This is 1 or -1 at random, half and half. And then if I is 1, we draw from the population. And if I is -1, we draw from the model. And then the discriminator has to predict, is it model or is it population? That's I. So we draw a pair, IY, from this distribution where this is either from the model or from the generator, and I says which it is, and the discriminator has to predict which it is from the image. Okay, now it's obvious when you look at this, I think it's obvious to most people, that if the generator is not perfect, then the discriminator is going to be able to do better than chance. If the generator is perfect, if it's drawing exactly the same probability distribution, then the discriminator has no grounds for getting the answer correct, right? The discriminator can't do better than chance if the generator is exactly correct and it's exactly sampling from the population. So if the discriminator model is perfect, the only way the generator model can make this loss can fool the discriminator is to exactly model a distribution. So assuming that both of these models are completely powerful, there's a trivial theorem that the generator has to converge on the exact distribution. So that's the universality assumption. And this, when GANs first came out, a lot of, especially people in the learning theory community, laughed. They said, "This is silly." The assumption that these models are that strong that the generator is going to learn to model a distribution perfectly by fooling a discriminator. That theorem that this is going to converge on the population distribution is assuming that the models are universal. And what I mean by that is not only can they express anything, the exact distribution, the discriminator can always tell if the generator is not perfect, and the generator can become perfect, was a ridiculous universality assumption. And it is ridiculous, except that it turned out to kind of work. It turned out to be useful. So the moral here is that the universality assumption is useful, no matter how silly or crazy it is. To assume the universality assumption is assuming that these models have the expressive power and can be trained to find what they're looking for. It's not true, but it's a useful way to think. It's a useful way to design things. So I've already said that this universality assumption is false, but useful. This is another slide that's not terribly important, but when GANs first came out, it was a little piece of theory that was, easy to derive about GANs. And that is, if you take this is the GAN objective, right? You've got the two players, the generator and the discriminator, and the generator is trying to fool the discriminator. If you say, well, suppose for any given generator, suppose the discriminator is perfect. If the discriminator is perfect, you can solve this by replacing the discriminator by the true probability of I given Y. So you just get rid of the discriminator by assuming the discriminator is always trained to perfection. And then you can ask, well, what's the generator that solves this problem? And it turns out you can break it down into cases depending on whether I is 1 or -1. And then those two cases, half the time you're generating from the population and half the time you're generating from the generator, those two cases turn out to be, it's possible to write them up to an additive constant as two KL divergences. And this sum of two KL divergences, it's a KL divergence in two directions, right? One from the population and one from the generator. And this expression in terms of two distributions, the population and the generator, is symmetric. Unlike KL divergence, this sum of the two in both directions is symmetric, and had a name from information theory called Jensen-Shannon divergence. So the generator is minimizing the Jensen-Shannon divergence, which is 0 if and only if the two distributions are the same. So this is saying under the universality assumption, the generator needs to converge on the true distribution. Now there's a problem. When somebody gave a talk on GANs at TTI, Avram Blum was in the audience, and he said, well, suppose the generator, if it's an arbitrary model, just samples from its training data. Now, if the generator is able to just sample from its training data, it's going to be very difficult from the discriminator to tell that those aren't real images, because they are real images. It's just that they're taken from a finite sample. And that finite sample means that you're definitely not modeling the space of all images, because no finite sample covers all images, but it's going to be very hard for the discriminator to tell that those aren't real. So this problem is called mode collapse. It is possible for a GAN to fool the discriminator without covering the space of images. And this is a real phenomenon. And we'll talk about sort of proof that this happens later. So this is called mode collapse. In practice, the generator can be generating a subset of the distribution, but a subset of images that look very natural and the discriminator can't tell. Now, we don't have cross-entropy loss, so there's a literature on GANs, and in AI, in academic AI, people compete on performance. I mean, what choice do you have? You have a leaderboard and some evaluation. So for GANs, you don't have cross-entropy. So it has become standard to evaluate generative models, not just GANs, but diffusion models, any generative model of images or sounds, by a measure called FID, Frenchel inception distance. And this is still standard it's still a standard measure of how well a diffusion model does, for example. So I've already said this, we can't use cross entropy or KL divergence. So what is this Frenchel inception score? So the Frenchel distance, I have a lot of these technical slides, but bear with me. We can define a Frenchel distance between two probability distributions. So this Frenchel inception score has two pieces. There's the meaning of the word, I keep saying Frenchel, it's Frenchet. The Frenchet inception score has two pieces, what it means to be Frenchet and what it means to be inception. So first, I'm going to define what it means to be Frenchet. So the Frenchet distance between two probability distributions is a kind of what's called an earth mover's distance, or a Wasserstein distance. So we imagine taking so say we got a distribution of two images, and they're assigning different probabilities to these two distributions are assigning different probabilities to the two images. And I want to know, can I transform this distribution into this distribution by moving probability mass from images under the P distribution by moving the probability mass around, can I convert it to the Q distribution? This is earth mover's distance is motivated by considering piles of dirt, and you've got some initial distribution over the dirt, and you want to move as little dirt as possible to produce a new distribution, a desired placement of the dirt. That's called the earth mover problem. So the motion, the moving motion, is represented by a joint distribution on the 2 points. So this is saying, given X, there's a conditional probability. I'm going to have a joint distribution, and there's a conditional probability of Y given X that's telling me how much of X moves to Y. So I can think of the motion as a joint probability distribution on X and Y. And so when I sample from this joint distribution, I'm sampling a motion. And the earth mover's distance here is saying, what's the L2 distance between a point and where I moved it to? So when I sample here, when I sample from this distribution, I'm getting a point and where I moved it to under the earth mover analogy. This is a distribution of a point under X and a corresponding point Y. And you look at how far it moved, the L2 distance it moved, and the average L2 distance moved, and you take the square root of that, and that's the Frenchet distance. It's a form of earth mover's distance. Apologies for I just feel obligated to write the equations. So that's Frenchet. Then what is inception? So in the FID score, inception says we take an image, and instead of moving the image in the Earth Movers thing, what we're going to do is take the image and pump it up through the inception network. That's a vision network. I think it was 2014-ish. And we're going to take a layer in that ConvNet, and that's like a feature map for the image. And instead of measuring the Frenchet distance between images, we're going to measure the Frenchet distance between feature maps. So we're going to measure so it's the Frenchet inception score. It's the Frenchet distance between two distributions on the inception features. And you can think of Earth Movers distance as related to finding bipartite matching. We want to take an image from one distribution, say the image generated by the generator, and a corpus of natural images, and finding a match, finding where to move one image to the other image. And that's how it's measured in practice, by finding some kind of matching. Okay, now I'm going to shift gears a little bit and just do a historical timeline of GANs. So now we know what a GAN is. GANs were introduced in 2014. This is the first paper on GANs. So here we're modeling the distribution of MNIST digits. This is back in 2014. MNIST was still a reasonable thing to talk about. I get very upset when I see a paper now that talks about MNIST. But what we're seeing here is samples from the GAN, and there's this issue of is the GAN just sampling from its training data? So what's in this last column is the nearest neighbor in the training data to this last image that was generated from the GAN. And so we can do it on MNIST. Now it's much more interesting to do it on faces. So we're doing the same thing. We're generating faces from the generator. We're feeding random noise through this network. And then this is the nearest neighbor in the training data to this particular generated image. Okay, so GANs really took off in the mid-teens. GANs were a big deal. DC GANs was a big step. These are bedroom scenes. These are generated bedroom scenes. Then there was these games people played. This is similar to previous to this, there were word embeddings, vectors associated with words of English. And if you took the word for king and subtracted the word for man, every word has a vector. So you say king minus man plus woman, and you get the vector approximately for queen. So you're saying that these vectors have components that you can separate. So this same phenomenon was then demonstrated for GANs. So how does this work? So for GANs, all we can do with the GAN is generate an image. So we generate an image, we've got the random noise vector that it was generated from. So we can think of that noise vector as a feature vector that the GAN is assigning to the image that it generates. All right, so by generating a bunch of images, we get a bunch of images, each one of which has the noise that it was generated from. So you can think of those as image vector pairs. All right, so now we've got a bunch of image vector pairs. Somebody goes through a bunch of generated images and collects all the men with glasses. We take the mean vector for men with glasses. We generate, somebody classifies the images. These are all the images of men without glasses. We take the mean image for men without glasses. We subtract the mean image for man from the mean image for man with glasses, and we add the mean image for woman, and we get women with glasses. Strange, but kind of fun. It sort of suggests that the vector that the GAN is generating from carries some semantic information about the image, and we'll talk about that at the end. Here's another thing you can do with the GANs. We can generate two images. in this case, we're looking at the image here and the image here. We're generating two images. This image has a vector, the vector that it was generated from. This image has a vector, the vector that it was generated from. And we can gradually interpolate one vector into another. We first start with just this vector, then we average that with a little bit of the other one. Then we average it with a little bit more of the other one, and so on until we've got just the other vector. And for each intermediate vector, we can generate an image from it. So these are all images, and we gradually convert this image to this image. We can interpolate. Some of these images aren't very attractive, but we can interpolate between faces. Okay, now I've said that the fundamental motivation for GANs, or a fundamental problem that GANs are addressing, are these very high entropy continuous distributions like images or sound waves, where autoregressive models are difficult. We don't have a softmax operation over continuous spaces to build a conditional model. But there are cases when the probability distribution over an image is really crisp, and we can sort of use a cross entropy loss. So consider video, and consider predicting the next frame of video from the previous frames. So I want to consider predicting, oh, that should be t plus 2. I want to predict t plus 2 from t and t plus 1. I want to predict a third frame from the previous two. So we're trying to predict yt plus 2 from yt and yt plus 1. So yt and yt plus 1 in a video frame are both going to be very similar to yt plus 2, but the reason I want two of them is so that I can see the motion. And if I know the image and the motion, I should be able to almost exactly predict the next frame, or very closely predict the next frame. So in this case, it is possible to use a form of cross entropy loss. I can make a next frame predictor. The next frame predictor is going to predict yt plus 2 from the two preceding frames, and then I can just look at the L2 distance between these two images, where the images are viewed as vectors. An image is just a very high dimensional vector. And now I can actually train this kind of model. So a conditional image model where the conditional density is very sharp, such that L2 distortion on a prediction makes sense, is we can get close enough that L2 distortion works, we can start using L2 distortion between a prediction and the actual ground truth image. And I'm going to generalize this to any conditional image distribution, right? So I'm going to have XY pairs, and think of X and Y both being images now, where the image Y, the image X contains enough information that it's possible to produce a Y and then measure an L2 loss. And we could also use L1 loss. L1 loss is, you take the vector, the L1 loss is taking the sum over the components of the vector of the absolute value of their difference. I just write that as the L1 loss. Okay, now we're up to 2016. So this isn't a lecture on GANs. I've just gone back to cross entropy, right? I'm saying in certain cases you can use cross entropy. But it turns out GANs are going to be helpful here. So there was something called pix-to-pix. You can probably still bring this up and use it. Pix-to-pix is trained on pairs of images. We've got a pair of image XY. So here we might have a segmentation image. This is called a semantic segmentation. It's classifying regions as either road or street lights or cars or sky or tree. So this is called a semantic segmentation. We can take an image and generated semantic segmentation, either by having a person do it or by a off-the-shelf segmentation algorithm. Now I get a pair of these things. Now what I can do is I can take one of them and conditioned on that one, try to generate the other. So I could train a segmentation algorithm from a pair of human segmented images where I have image and segmentation. But there are lots of cases of pairs of images. Here's colorization, black and white to color. Here's line drawing to a different form of drawing, a full fleshed out drawing. Day and night, aerial photograph to map. So there are lots of cases where you have these pairs of images. Now, this in Pix2Pix, this image translation, you can think of this as a translation problem. This image translation was done with something called a UNet. And UNets are fundamental to diffusion models. And hopefully we'll talk about exactly what a UNet is. But it was developed in 2015 for image segmentation, for an image-to-image translation process. Okay, now what we can do is we can combine our L1 or L2 distortion loss when we try to generate X from Y, or sorry, try to generate Y from X. We can add a discrimination loss. So what does that discrimination loss mean? It means we've got a pair of images. The discriminator sees X, right? So we've got a discriminator. It sees X, conditioned on X, and an image Y. Now the image Y is either the actual image that was paired with X, or it's a generated image generated from X by the translator, by the generator. So the discriminator is saying, was this the prediction made by the conditional distribution, or was it the actual one? And if the prediction is not perfectly modeling the distribution, this discriminator loss will drive the generator to be closer to the distribution. So if you can add a discriminator loss to a cross entropy loss or L2 loss, and it will do something helpful, useful, especially in perceptual realism. It will definitely improve the perceptual realism of the predicted image, because that's what the discriminator is going to look for. Is this plausible? Does it look like an actual image? So now what this paper does is it compares various things. So you have just using the L1 loss. L1 tends to do better than L2 in making the images sharper, so they tend to be better. You can use just the GAN. The GAN is all you use to model the accuracy of the generator, or you can use a weighted combination of the two. So here we have the results. So this is an input segmentation. In this case, we're generating an image from the input segmentation. Here's the ground truth. This is the actual image that the segmentation was generated from. And here's 3 predictions, and one is L1 plus GAN. So the combination of the two, both in terms of intuitive judgment of how good these images look, and I believe in terms of FID, is an improvement. So this is an application of GANs as an addition to an L2 or cross entropy or L1 loss. So these are just more examples. Okay, here's another place where a discriminator loss helps in addition to an L2 or distortion loss. So this is unpaired image-to-image translation. So here we have, let's say, a bunch of images of horses and a bunch of images of zebras. And what I'm going to do is write two models. One model takes an image of a horse and produces the corresponding model where the horse has been changed to a zebra. The other model takes an image of a zebra and predicts or converts it to another image where the zebra has been converted to a horse. Okay, so at a very abstract level, I've got these two distributions, horses and zebras. I have no translation pairs. So this is unsupervised, it's called unsupervised translation. We've got corpuses of horses and corpuses of zebras. And I want to train a translation process. So what I do, this is called a cycle loss. So we take an image, say, of a horse. Our model transforms it to an image of a zebra. The other model, so this is the horse to zebra model, the other model translates the zebra back to a horse, and then I can look at either the distortion, I can look at the distortion between these two images. I mean, if this was a really good model, these images should be very similar, right? You put stripes on, you take the stripes off, you should get the same thing back. And this is called a cycle consistency loss. It turns out you can view this as something we're going to study later. A different kind of model we'll be talking about later. But this can be viewed as a latent variable. The zebra can be viewed as a latent variable for the horse. So a VAE, a variational autoencoder. This is a form of variational autoencoder. But you can also add a discriminator loss to this. So in addition to doing the cycle and looking at the distortion or some kind of cross entropy loss, I can add a discriminator loss. So this is, again, adding a discriminator loss to something that can also be evaluated with a cross entropy or distortion loss. So that's why it's called cycle GANs. GANs were very popular, so the GAN nature of this was what is emphasized in this paper. And you're looking at a cycle consistency loss. So here we have the image translation, right? So we've trained a model to convert a horse to a zebra. We've trained a model to convert zebras to horses. But it doesn't always work. I mean, everything has its problem. This is horse to zebra applied to Putin riding a horse. And we can see that there's a problem here. Okay. I talked about this cycle loss in the context of horses and zebras, but it turned out in about 2017, people discovered that you could use this for two languages, in particular, English and German, or English and French. Those languages are pretty close, not like English and Japanese. And it turns out that if you train a translation system from English to German and a translation system from German to English, no translation pairs, just a corpus of English and a corpus of German. And you just and you're training a model to go from English to German and another model to go from German to English. And then you're looking at a cycle consistency. And for language, we have cross entropy. We have these autoregressive models that are giving us cross entropy. So in the language case, it was just cross entropy. But it was discovered that you can actually train a non-trivial German to English translation system by just using the cycle loss. Okay, progressive GANs. This was a big advance in GANs. Now, faces are the easiest, we've talked about this before, faces are the easiest thing to model in images. But cycle GANs was the first system that could produce really high quality images of faces. You know, this is where the headline said, these models do not exist. So in a progressive GAN, you train you train a sequence of images of increasing resolution. So we're starting out with very small images and gradually increasing the resolution of the image until we get a high resolution face. And what we do is we put a discriminator at each stage. So there's a discriminator. We take an actual image, we downsample it to a small image, then we take, so we get a distribution on low resolution images. And we ask the discriminator to discriminate the low resolution images from the actual low resolution images from the generated ones. And there's a discriminator at each level of this progressive GAN. So you're training a GAN at every resolution. And this really helped the models. Okay, this is for faces. Now, suppose we want to do general images. So this is back when that was hard. And if you just take GAN and train it to produce images from ImageNet, this is the kind of thing you get. Sort of nonsense, you know, many heads. But this in 2018, so now we're getting to be reasonably recent, 5 years ago, 6 years ago. In 2018, class conditional GANs for the first time could produce images of dogs and, you know, landscapes and hamburgers. So this was a big advance, and this was a pure GAN, class conditional. So class conditional means that you train a GAN for dogs. You train a GAN, a completely different GAN for scenery. You train a completely different GAN for butterflies. Okay, then we get the style GAN, 2018. This was a big advance again. The images here are much higher resolution, and they're much more impressive. It is also, this style GAN is also a form of progressive GAN. It's generating images of increasing resolution. And I think there's a discriminator at each resolution, but the particular architecture is more sophisticated. The noise is being, instead of just taking a noise vector at the input, you've just got a constant input and you're injecting noise. You're injecting very highly shaped noise, shaped by a big network, and then injecting it at the various layers. And these are called style injections. So now what we can do is we can take images. Each image has a noise vector, a style vector being inserted. So we can take the coarse style vector from one image and insert it into a different image. So here we're taking images and transferring style. So we've got, these are real images. These are real images. What we're doing is we're taking this image. This is a generated image. These are all generated images, so that we have, for each of these images, we have all of their styles. And I can take this image with all the, and take and replace its coarse style with the coarse style of this image. So I'm replacing this, the noise that's generating this image, with one component of the noise that's generating this image, the coarse style. And so, you know, you see that the coarse style is determining age and gender. But I can also take not the coarse style, but finer styles. This is the medium style is taken from this image. And here, this is the fine style taken from this image, the high resolution noise. So if we take the high resolution noise, we pretty much preserve the identity of the image, but we've changed some high resolution property, some high resolution noise. And it's weird, you can, I mean, what's happening if you change the noise a little bit, you can move the position of the hairs in the head while still preserving the naturalness of the overall image. So there's noise being added here that's filling in detail like where the hairs are in the head. And in 2021, a version of StyleGAN came out that was doing class conditional GANs and getting very impressive images of horses and cars, and faces are the easiest thing to do. So the horses and the cars were not as impressive. Now let me go back to this issue of mode collapse. So one of the things that came out of the later StyleGAN work was a GAN inversion method. So you'd take a given image, and by solving an optimization problem, you could search for the noise vectors that generated that image. And if that image was generated by StyleGAN, then you could, by optimization, find the noise that generated that image. And that's called inverting the GAN. Finding the GAN generates, you're finding the noise that generates a given image. So you're inverting the GAN. And I'm writing that inversion as the GAN inverse. This is taking an image and giving you the noise that generated that image, and then generating from that noise. Now, it turns out that this inversion process works accurately if the image was generated by the GAN. If the image was not generated by the GAN, you get a really significant distortion. No matter how much you try to invert it, the GAN just isn't capable of producing that image with high fidelity accurately. So it says that yes, a random image is not in the range of the GAN. It's not a typical random image. The GAN will not be able to generate that image. So there is mode collapse. It's sort of like hand designing a discriminator that wins the game. Okay, in 2023, so now this is quite recent, there's another paper showing that if you build a GAN inverter for StyleGAN, you can take the vector that the inverter produces, the vector representation that the GAN inversion produces, and extract useful features from it. You can extract depth maps and surface orientations and lighting. So it's sort of like in language, you train a foundation model by cross entropy, and then you show that that foundation model can solve lots of downstream tasks, either by fine tuning or by finding projections of its vector. So this demonstrates that that idea of training a foundation model that then supports other things exists in pure GANs. You don't need a cross entropy loss or variational autoencoder loss. And I'll end there. And next time we'll start talking about variational autoencoders.